through the Learn Smarts and to get through the homework. Okay, that's your power through. You picked up today the lab that we're going to do when I come back next week. So your job while I'm gone also is just to do this first page, which is your pre-lab, and sort of look through the lab. The lab is in the book. There were too many drawings. I wasn't going to try and redo the procedure, and it's pretty okay for this lab. So make sure you look through the lab. We are going to be working with some heavy chemicals, some heavy metals in the lab, so make sure you understand how the lab is going to work. Okay? Other than that, then next time is just a work day, so you got this lab and your Learn Smarts and your homework to get done. Okay? Let's go ahead and get into, I had you bring up your Canvas for both Weber State and for DSD, because at the very end, I'm going to do a Nearpod, and I'm going to hit and miss on the Nearpod, but it's going to reflect on your citizenship grade. And what I'm going to do is I want to see what you have accomplished in the class. It's sort of like a hold you accountable for getting your Learn Smarts and your homework done, because I'm seeing a lot of kids that aren't getting them done in class. So I want to see what you're doing. Does that make sense? So I'm going to hold that on your citizenship, because I can't put it on your grade. So as long as you're working and getting things accomplished in class and getting things done instead of just talking and not getting stuff done, then you're fine. Okay? It's just a way to try and help motivate you to get stuff done. All right, and I'll show you that towards the end of the period. All right, so we're going to go on. Did we stop at 14? That's where most of the other classes start, but I thought we didn't get as far in this class. Was it 14? Okay, so we're going to start at 14, and we'll go on there. Did we actually do these, or do we need to do them? We need to do them. Okay, so I put colored pencils out because this, when it's covalent bonding, I like to have the colored pencils so I can use different colors for different elements. So first thing we do is we do the Lewis dot for each of them. So hydrogen has how many Lewis dots around it? 1. Good. And fluorine has how many? How many Lewis dots does fluorine have around it? You might want to get your periodic table out so you don't have to crank your neck all the time. And if you're on the back row, you might want to turn around. Okay, 7. Remember, you've got the boards on the side here. You're welcome to grab those if you're on the back, so you can do that. So what we're going to do here is, these are not ionic. It's not a give and take. So they're going to share equally or share polarly. One gets a little bit more than the other. Fluorine is going to come here and sort of flip a little bit, so it has its opening over here. And hydrogen's going to come in right here and bond here. We want to have the one that would have the more positive on the left, and the one that would be the more negative on the right. Doesn't mean they're going to be a full negative or a full positive, but it would be what would be that way. Let's go ahead and do the next one. Carbon. How many does carbon have around it? 4. So 1 on each side, right? Okay, what about nitrogen? 5. So 1, 2, 3, 4, 5. Oh, we've got a conundrum. How am I going to make them both have 8 or 2, but that's not hydrogen, so they both need 8. We actually need to do one more thing, because I forgot to do this on here. This is actually added 1 electron. It's at one of our polyatomic cyanide. So it would have a bracket around it with a minus. That means it has 1 more electron. Can anybody see what we would need to do? How many does nitrogen need more? 3. So let's put 3 of nitrogens in the center. So here's nitrogen. I'm going to put 3 of its electrons in the center, and I'm going to put the other 2 opposite. That means carbon would have to share 3, right? That leaves only 1 left over for carbon. Everybody okay with that? The last one for carbon comes from right there. Oh, let me take this just a second. It's one of the other teachers. She must be running late. Hello? Yes.
This is Colleen.
Sorry for those that are listening online. Okay, sorry. Interruption. Okay, so this actually fulfills both of them by giving the carbon 8 and the nitrogen 8, right? And we'd actually rewrite that by just going dot, dot, C, line, 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 N, dot, dot. And since we added an extra one, we have to put the brackets and put the extra one we added on the outside. Okay? So now we go to this next one. We have a carbon again. We just did that one up above. Carbon had 4. And hydrogen had 1. Now we've got 2 carbons and we got 4 hydrogens. So I'm going to put the 2 carbons in the center. And I'm going to put the hydrogens on first. I'm going to divide them up evenly between the 2 carbons because I know they're probably going to split between the 2 carbons. So I know that there's going to be a hydrogen coming here, and here, and here, and here. And I'll put my hydrogens on because I'm going to change colors. And wherever the hydrogens came on, they're going to have to share an electron with that hydrogen. Now I put them off at an angle like this because I know what's going to happen. You probably wouldn't be able to do that if you didn't know what was going to happen. But each carbon has used 2 of its 4 electrons. So it has 2 more that it can share. Right now, each carbon only has 4, and it needs 4 more. So if it shares its 2 that it has left over with the other carbon, then it would, so I'm going to have this carbon be this, and I'm going to put X's for this carbon so you can sort of see where each one's coming from. Okay? So each of these carbons now have 8 around them. Can you see this? And this one has 8 around it. And each of the hydrogens have 2. So we would then rewrite it like this. H, C, double C, H, put another H down here, another H here. This one doesn't have to have any, or doesn't have any unshared pairs of electrons. Every electron is being shared. And I guess I should have done this one up here. This is H, and then it would just be like that. Okay, then we get to sulfur. Sulfur has 6 around it. And I'm going to do 2 different sulfurs because that's what it says I have. Each one has 6. They need 2 more. So if they share 2 between the 2, then they'll be able to get to the 8. So share 2. The other sets are going to go at an angle of a triangle, if you can see that triangle. And we've got the other sulfur. So they want to be 100, it'll be 180 or 120 degrees away from each other. So again, this one has 8. This one has 8. Okay? So and we're done. Now, we okay to go forward? Everybody understand how I did it? Does anyone need me to go back? We're okay? All right. So going forward, we've got a few more that we need to do. I would like you to do on your own this one, and this one really quickly. I will do the others with you because they're a little tricky. But go ahead and do water, ammonia, and methane. So H2O, NH3, and CH4. I'm going to give you a few minutes to do that. I'll put a little square around them because that little... So do this one, and that one. If you need help, I'll come around and help you. Is the witch in your way, Julian, when you're trying to see? Is the witch in your way? Okay. If she is, let me know and I'll move her. Okay, do not look up until you've got those done. I'm going to put them up really quickly, but I want you to do them on your own, and you can check them with what's up here, okay? Okay, if you finished them, go ahead and go back and give the, excuse me, do the Lewis dots for just the elements in the other 3 boxes. Just write down the C, the O, write the Lewis dot is for them, the C, the H, what the Lewis dot is, and the S and the O, and what the Lewis dot is for it. Excuse me. Okay, is everybody up with me? Okay, so if we look at CO2 on the top, we only have 1 carbon, and it's going to go in the center because there's only 1 of them, and so the oxygen is going to go on either side. Now, we look at oxygen, each oxygen needs 2, and carbon has a total of 4. So it will give 2 to 1 and share 2 with the other. So I'm going to put carbon in the center, and I'm going to put 2 electrons on either side of it, like this. Then I'm going to bring the oxygens in and have it share 2. And it's going to have 2 other pairs that it doesn't share on both sides. So when I draw it with the lines, it would be like this. So now if we look at the next one, and I've drawn each of the Lewis dots out so I know how many of each I've got for these now. If I look at the next one, I have 2 carbons, and each of them have 4. And then I only have 1 hydrogen for each carbon. So if each carbon gets 1 hydrogen, that leaves 3 unpaired electrons.
Okay, so what are the numbers on it? 1, 2, 3, and 4. Is that the terms?
It should be 1, 2, 3, 4 as far as drawers.
No, like there's numbers on the top.
It should be, sorry, excuse me for a sec. Back, and if there's not enough room, take some of the out of the very back and just go through. Okay, so carbon and carbon have to share 3 each in order to get to 8. So I'm going to put a carbon here, and I'm going to use this one X's so I can show where they're coming, and I'm going to use the other one as dots so you can see where it's going. And then I have a hydrogen coming in here and a hydrogen coming in here, and you can see then each carbon's going to have 8 around it. You see that? And each hydrogen too. So when I rewrite this, it'll be H, line, C, line, 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 C, line, H. There's no unshared pairs of electrons. Okay, now this next one gets a little tricky. You have a sulfur and you have 3 oxygens, and all of them only have 6. Well, because the sulfur is only one of its kind, it's going to be our center. So whatever is unique or one of its kind is going to be the center. So I'm going to put it in the center. And the first oxygen that I bind, I can say it's going to take 2 of the sulfurs and share 2 with it, and then I'm going to have oxygen like this. That's how we bond before, right? So we know it's going to be a double bond. But now I've got 2 more oxygens that each need 2 electrons. So the bond that if the other 2 oxygens form with the sulfur is what's called a coordinate covalent bond, in which sulfur donates both electrons to that bond. In other words, oxygen's being a little bit of a bully and forcing sulfur to share those with him without doing anything for him. So oxygen's going to come in here, share those two, and retain its 6. Oxygen's going to come in here, share those two, but retain its 6. So when we go to look at it, sulfur in the center is going to do a double bond with one oxygen, but it's going to do a single bond with 2 other oxygens. And it will be a trigonal planar shape. It will lay in a flat plane and it'll be a triangle shape. Now, that double bond can be any one of those oxygens. And so because it can be any one of the oxygen, where any of the oxygens are, we call it a resonance structure, because it could be at the top, it could be on the left, it could be on the right, it could be depending on what molecule we've got. And we'll talk about resonance in here in just a minute more. We okay with this? You see how I sort of figured out how it was all going to make? If you look at each one of these, each one, like all the oxygens, have 8 around them. Okay? And the sulfur also has 8 around it. Okay? All right, going forward. There are exceptions to the octet rule, and you got to know which ones they are. Basically, it's boron, phosphorus, and sulfur. Boron's column itself can be there, but boron is the only one that's going to covalently bond because it's a metalloid. Okay, so whenever I do boron, I just know it's going to make 3 bonds. So I'm going to come out with fluorine because fluorine needed 1 each, right? And I'll have a fluorine here, and a fluorine here. Well, guess what? When it does it with hydrogen, it's going to do the same thing. So you show me what hydrogen looks like. Or boron trihydride is how we name that one. Hopefully you came up with just boron in the center, a hydrogen, and a hydrogen. So it's about a 120 angle, right? There's no unshared pairs of electrons. Boron does not get to its 8, but it comes as close as it'll ever get because that last room, that last p orbital is not open. Okay, so I'm going to leave this one for you to do, but I'm going to show you how to do it on this one. So sulfur has 6 around it, right? And fluorine has 7. And fluorine is one of those very, very aggressive elements on the periodic table. It will take what it wants. So it wants 1, it's going to take 1. So sulfur sits in the center and says, okay, fine. I'm a party animal anyway. And so I'm just going to show you with the dots here. Since we have 6 fluorines, 1 fluorine is going to come in here, make a bond. 1 fluorine 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 here, and make a bond. So it forces sulfur to do some funky things. So when we actually write that, so this is just me writing it to figure it out. When we actually write it, what happens is sulfur is in the center. A fluorine is going up, a fluorine is going down, and then on a plane, a square plane, there's a fluorine here, 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 and here. So it looks like that. So like you've had a pencil with a paper through it, or paper with a pencil through it, okay, is what it would look like, and on fluorine on each corner of the paper. I want you to try and do this one. Okay. P.S. by the way, they do it their way. Not the right way, but they do it their way. Oh, it's not up. It's not up. I'll get it when we get in. Just remind me before the end of the period.
We checked in at the office.
Okay. Then it should override it. Make sure you pick up the lab on the table that you'll need to do the pre-lab next time. I just wanted to make sure everybody got one. Not have that sub not pass it out. Okay, give you a few more seconds here, see if you can get PCl5. Heard you had some gremlins in your car. So this is what this looks like. You should have had all the chlorines took one of each of the phosphoruses electrons, and it actually makes, if you made a paper that was triangle shaped and you stuck a pencil right through the center of it, that's the shape it would be. So both of these, the phosphorus and the sulfur, do more of a top-like shape where one's a square top and the other one's a triangle top. If that makes a sense. Okay, so going forward. Resonance, like I told you earlier with the SO3, is when the true structure of the hybrid is the resonance of two or more structures. Resonance stabilizes a molecule by spreading out the lone pairs. So it tries to make it more, it doesn't really spread out, but we'll see in just a minute. And the electron pairs in a multiple bond over a larger region of space. A molecular ion that has two or more resonance structures is resonance stabilized. So it actually, instead of looking, when we look at it through different means, sometimes it looks like it almost has like a 1.5 bond instead of a full 2 bonds or 1 bond, because the double bond shifts. Or in different structures, it's in different places. So it ends up coming up looking like it's a 1.5 bond or a 1 1/4 bond, which we know really isn't there. We okay to go forward? I know there's a lot to write down here. And I will be putting this up on Weber, so those of you that missed it, you can go back. Okay, so these are ones that could possibly have resonance structures. So let's look at what we could do here. So for the first one here, hydrogen has 1, carbon has 4, oxygen has 6. So now I'm starting to shortcut. I'm not writing everything down, okay? So I'm starting to shortcut. Since carbon's in the center, I'm assuming that's going to be the center molecule. So I'm going to put it in the center. And I might have to move around its Lewis dots, but we'll start there. I know hydrogen, when it comes in, is going to take one of those bonds. So here's my hydrogen coming in, and it takes 1 bond. Now, I've got oxygens coming in. I've got 3 oxygens, but I only have 3 electrons, and I know that each oxygen needs 2, right? So this one is a little bit hard because as I'm looking at it, I'm saying, okay, I'm going to have an oxygen. If I put an oxygen here and it comes in, I'm going to have 1 extra spot. I'm going to have an oxygen here and it comes in and it has 1 extra spot. And I have an oxygen here and it comes in and it has 1 extra spot. So how can I redo this so that can actually work? Well, what if I don't put the hydrogen on the carbon? So see how I'm thinking through this? I've got to figure out how this goes together because this is a polyatomic. What if I put that hydrogen on one of those oxygens? So let's take that hydrogen off right here and now put it, let's say, on this oxygen right here. That fills the place, right? Now I have this extra electron. I can move that over and make that right here with this oxygen be a double bond. So it will share 2 with 2 of this oxygens, and now that oxygen doesn't have any to worry about. Now I just have this 1 oxygen that's hanging out that needs 1 extra. You see how I'm thinking through this? Well, I had 1 extra right here. I should use it green because I haven't used green. Okay, it's right there. So that one actually comes in and fills right here. Now I'm going to redraw it so that I'm showing with just the lines as the bonds. So can you see how I thought through this? Because you're going to have to think through something like this. Okay, so I'm going to have an oxygen, has 2 extra pairs of electrons, double bound to a carbon that's single bound to an oxygen that has 6 around it. That's single bound to an O, that's single bound to an H. And it has 1 extra electron. Well, when they say there's a resonance structure, I could also have drawn that, whoops, that arrow is double-sided arrow. I could have also drawn that like this. I could have put the OH up here with a carbon here, with a double-bound oxygen down here, with a single-bound oxygen up here still. And it would be a -1. So there's different ways I could draw it, but it's the same molecule. And because there's different ways I can draw it back and forth, and I kept that oxygen right there, I just flipped these two. It's what's called a resonance structure. Okay? I didn't just flip it like this. You see what I'm saying? I didn't just twirl it, but I actually moved those 2 places. You see that? So that makes it a resonance structure. Okay, we did SO3. I want you to try and do SO2. Okay? SO2. And this should have been at O3. And if you get done with SO2, try O3. I'm going to put it up in a minute, but I want you to try it. Go through the same process that I did. Try and figure it out. Sulfur is going to be your center molecule. Yes, ma'am. Okay, first of all, get this one copied down so you have something up there that's an example. And then when you get that copy down, I'll come back. Come on, keep going.
Is there any way you can give me the password for the test that we just took to review my answers to go with my tutors?
I can see. I think she only opened it for 30 minutes after. So I might be able to, let me see what I can find out to do.
Because it's at Weaver Davis campus.
Yeah, I know. It's just, they're really particular about letting tests out. So I might be able to tell her give you a list of things like you missed, but not the exact.
Okay.
Because they usually don't let you review it after you're out of the testing center. Okay, again, do not look up until you are convinced you've got it right. If you've got the SO2, I want you to try the SO3. Here's a hint. It's sort of the same, right? Okay, can you see how they would be resonance structures? Remember, I'm just flipping one thing. The unshared pair of electrons counts as sort of like a bond because it's not shared. That is remember I called it a ghost. It has its own space. So because of that, it does make it a different kind of thing. It's not just spun in space, but I switched where the double bonds were. Okay, so that's what what is meant by resonance. Okay, so when we look at O3 or ozone under, we look at the bonds, it actually looks like in between each of those oxygens there's a 1.5 bond because that double bond keeps flipping where it is. So as we look at it, because we look at so many, it looks like a 1.5 bond, but it's really not. It's just the double bond keeps flipping where it is. Okay, that's resonance. So it's like one of those old-fashioned, I don't know if you've ever seen the old-fashioned paper things, but you look and you see each one separately, but if you put it together, it looks like it's a motion picture. So, you know those old-fashioned cartoon books. Okay, so going forward, this is how it affects human body. There are many covalent compounds that are related to the chemistry of the heart. You've got glycine, is a building block of the protein that composes the heart muscle. You've got nitroglycerin that acts on the muscle walls of the blood vessels, increasing the blood flow in oxygen delivery to the heart. You've got the protein hemoglobin in the red blood cells that binds the covalent molecule O2 and then carries it throughout the body. And then you've, the principal component of all the blood and bodily fluids is water. And so water is also a covalently bonded molecule. So put down a couple of those so that you can remember them. This picture is also in your book that you've got online. So as you do your Learn Smarts, you can look at this picture again because it is in your book. Okay. I'm going to go ahead and go forward. Again, this picture is in your book, or this will be up online as you need it. Another thing is we look at ozone. We just did the molecule for ozone, which is O3. It's formed when in the upper atmosphere when O2 atoms react with UV. It acts as a UV shield to the Earth, and you can sort of see where the ozone layer is in comparison to the stratosphere and the troposphere. It is a buffer for us, and there is holes that have been found in the ozone layer that have been growing because of pollution and that, and so that's something that you need to be aware of. And you've probably heard about it with your earth science or in biology. Okay, so now we're to naming covalent compounds. Yes, ma'am? For 1 second. Ready? 1,000. Okay. All right, this is going to be a cautionary tale for you guys. Once kids learn how to name covalent compounds, they want to name everything that way. You can only name a nonmetal with a nonmetal or a nonmetal with a metalloid this way. This is the only area that you can do it, and it's above the diagonal in the P. Okay? And it has to be just 2 different elements. If it's 3, it doesn't count. Okay, you have to name it type 1 or type 2. So I call this type 3. Just remember, because I'm going to caution you before I even start on the next slide, everybody, once they learn this, tries to name everything this way. Don't. Okay, it's easy, but it's not the way the rest of the table is done. Okay, so this is how you don't do it. You guys already know how to name this. Tell me what CO2 is. What do you call CO2? Carbon dioxide, CO2. 2 oxygens with 1 carbon, right? What do people get if the furnace doesn't work? Then they get this poisoning, which is CO. Okay, so it tells you how many of each. So mono, we only use mono if it's on the second one. I didn't say mono carbon dioxide. I just said carbon dioxide. And you said carbon monoxide. So I'm telling you how many there is on the second one if there's just one. Now, we do use things that have more than 1 element on the first thing. So like, for instance, dinitrogen pentaoxide. I'd have 2 nitrogens with 5 oxygens. Okay? So really fast and easy. My big caution is, remember, it's only for a nonmetal with a nonmetal or a nonmetal with a metalloid. You cannot use it on the rest of the chart. Really, really caution. Okay? So, the ending of the second one is still the same. Carbon dioxide, we change the ending to IDE, saying it's the negative one or the more negative one. The one that's closest to fluorine. Okay, so dinitrogen pentachloride, what would that be? N2Cl5, done. What would the name of P2O5 be? Diphosphorus what? I heard you. Pentaoxide. A lot of times we drop the A there and just go pentoxide. I'm not going to knock you down. If you do, just know that it's multiple choice. So the other three, really quickly, do them. This one isn't easy. You should be able to do it really fast. I'm going to do it slower, so when you get done, look up and check. Thumbs up, I got them all right. Thumbs down, I didn't get many of them right. And thumbs sideways, I just missed one. Okay, thumbs up, we're awesome. Woohoo! Okay, moving forward. See how many more you can do. And I'm going to have you guys come up and put it up. Have you put up 1, 2, on the board, 3, 4, 5, 6, 7, 8, 9, 10. Did you get your number done? If I gave you a number, go ahead and put it up on the board. And don't feel bad if you didn't get a number. You might get one next time. You should be able to use both pens at the same time. So if you're on the left side, you can do yours. So use one for the left and one for the right. Move fast. Okay, as they're putting it up, make sure you're checking. If they've made a mistake, quickly tell them and have them help them fix it if they did something not right. Okay, everybody's is up there. Give it a thumbs up if you think all of them are right. Thumbs down if there's not. And a thumb sideways if there's only one. And we have nobody but one person giving me a thumbs. They are all right. You did a good job. You did a good job. Just remember, normally when we name, and we don't capitalize, and this program, every time I tried to go in and write the name in, it kept trying to capitalize the first letter, and so finally I just gave up. Okay. Usually we don't capitalize chemical formulas. Okay, but you guys did awesome. Easy, right? This one's easy. Just remember, you can only use it for a metal and a non-metal. Okay, you have some more.
Are you picking more people?
I am. I am. And some of you might get to do it twice. So 11, 12, 13. 14, 15, 16, 17, 18, 19, 20.
Wait.
You're 18.
Six.
Hexa. Okay, as soon as you get yours done, go ahead and put it up. Again, try and get all these done yourself before they get them all up so you can do a double check. They should be coming really fast at you. If you'll notice, there's even more. Bromine? Yep.
I'm gonna forget. Can we take pretzels?
Uh-huh. You guys were late. You guys got late. Yeah, I gave everybody a pretzel. Happy Halloween.
Did you see my chocolate? Yeah, that's terrible.
Okay, but if you're just sitting down, get them done as fast as you can. See if you can beat them. Get them up here. If you get done with the ones that are on the board, move to the next ones. If you're one of the ones that put it up on the board, come back and sit down and get the rest of them done as fast as you can. Okay, this time I see 2 errors. There are 2 errors. If you can find the 2 errors, or find one of the errors, raise your hand. Okay, what is it? Okay, good. So remember the first one, we don't change the name ending on, so this should be chlorine. That was one of the mistakes. And it's okay, you were learning. Anybody find the other mistake? Yes. Yes. Not on the first one. If there's one of just the second, you should. Actually, there's mono, and there's actually one more. I didn't see that one, so good catch. There's one more. And it's a simple mistake. Well, all these so far have been simple mistakes. Last one is on number 18. Can anybody tell me what's wrong with 18? Should be an IDE on the ending. Yeah, the last one should have an IDE ending. Okay? So real simple mistakes, but you're getting the idea. Okay? There are more that you can practice. I'm going to pass through them really quickly to make sure that we get through.
That's crazy. On my paper, I would put.
It's all right. Okay, so we're going to go into the shapes. So you have some more that you can practice. So if you were struggling a little bit with that, go through and practice it. Check with your neighbor. Make sure they get the same answer. So you need to know the Vesper shapes. Oh, my heaven. Just a sec. We're going to go over shapes real quickly. Okay? Linear. That's pretty easy, right? Linear is a straight line. When you have two things, you're going to be linear. Sometimes when you have three things, you're going to be linear. Okay, so you need to make sure that if you end up putting it in a straight line, it's linear. Do you remember when I told you that they're going to try and trick you thinking it's linear and it's really bent? Okay, watch out for oxygen because they like to put the two unshared pair of electrons top and bottom, and it makes it look like it's linear, but it's not. So if you put the dots in like I told you, top, then this way, then go around and fill like this, it will put it in the shape that you see. Okay, and not the shape they want you to think it is. Okay, so we also have trigonal planar. This was like the boron trihydride and the boron trifluoride. Okay, we have tetrahedral. This is like methane, which was CH4. Okay, then we have where we have one unshared pair of electrons. That one is pyramidal, trigonal pyramidal. Okay, it gives you that kind of shape. So we call it trigonal, pyramidal, and it's a molecule. Notice my angle with one ghost is scared down by 2 degrees. Okay, we drop the 0.5 and it becomes 2 degrees smaller. If I end up with two ghosts, like water, remember, you got to be careful with this one because it looks like it's linear, but it's not. Okay, that's the one I was telling you about. This one will actually give us that shape. Okay, where we have a ghost at each of those corners of the tetrahedral, or an unshared pair of electrons, and we get a bent molecule. And the angle there is 105. So it's not a 90, it's a little bit bigger than a 90, but those are our main Vesper shapes that you're going to be responsible for, and you need to know. Okay? There's the others on there, the phosphorus and the sulfur. We'll take those funky ones, which is the trigonal bipyramidal and the octahedral shape, but you're not going to be really held responsible for these bottom ones. So that's nice. Like I said, this is the P and the S that do the funky shapes down here. And I think you have a copy of this, yes, in your notes? Okay. So I'll give you a few minutes to write them down then. I don't remember what got blanked out. Let me know when you're ready. Okay, we get all of them down in there. Okay, going forward. So, here I want you to sort of think about what kind of shape they would be. So, beryllium chloride. So just by the name beryllium chloride, what type? 1, right? So it's type 1. It has 2 bonding pairs. It has 2 valence electrons. It has no lone pairs. What angle would it have between its bonds? Beryllium chloride, the first one. It would be linear, so what would be the angle? 180. So you should have done 180 linear. Okay, let's look at the next one. Boron trichloride. What did I tell you about boron trichloride? What angles? We did boron trihydride and we did boron trifluoride. What angle was that going to be between those bonds? No. 120. And what shape was that called? Trigonal. Planar. Because it's all in a plane. It doesn't have any unshared pair of electrons. It had to have an unshared pair of electrons to be able to be pyramidal. Okay, methane, which was CH4, we've drawn it a couple times. So it has a carbon and 4 things coming off of it. No unshared pairs of electrons. What shape was that? What was the angle? Tetrahedral, and the angle was 109.5. Good. Okay, whoops. You didn't see that. Okay, NH3, which is ammonia, has 3 bonding pairs, 5 valence electrons, and 1 unshared pair of electrons. It's the 107. What's the name of it? Trigonal pyramidal, or trigonal pyramid. And then water. We've done this a couple times. Planar means in a plane. Pyramidal is a pyramid. This one is bent, and what is the angle? 105. Okay, so you should be able to, we didn't even draw the molecule, but you should be able to now, after we've drawn so many, get it thinking in your head, what does it look like? Okay, if you have to draw it out, great, do it. Okay, going forward. When we talk about electronegativity, this is how badly atom wants electrons. How much can it attract those electrons? So francium has the lowest want of electrons. It's 7 layers out. It's got so many electrons, it just doesn't care. But fluorine really, really wants an electron. So electronegativity is a power to attract those electrons to come to them. Okay? So you do need to know how that trends. The one that is the more electronegative of 2 elements will be the negative part of that bond. Okay? So, bond polarity. We have a lot of different ones. So last chapter we worked with ionic, which was type 1 and type 2. Okay? When we take their electronegative difference on the chart, there should be 1.9 or higher. A lot of times they don't get that high, though. We actually are down in what we call the polar covalent area. This is where we have unequal sharing of electrons, but one atom can pull it closer to them than the other one can, but they just can't rip it off. And that goes on the scale between 0.5 and 1.9. And then we have true polar, nonpolar covalent sharing, which is basically equal sharing. And there's no dipole movement. Dipole movement means I have a slight positive and a slight negative side to the molecule. And the electronegativity there, the difference would be less than 0.5. All right, so here's our water molecule. When we have a water molecule, we actually have a slightly positive and a slightly negative. And when we use a partial charge, it actually is a negative and a slight positive. That's the charge we use. It's a small delta. So in math, you use delta like this to do change. This is even smaller of a change than the big delta. So it's just a partial, just barely a charge, positive and negative. But it's enough that when you look at water molecules, they orient themselves so that you have a positive and negative next to each other, attracted to each other. Okay? As we look at different molecules, we should be able to say, okay, these are not exactly equal. So which one is closer to fluorine is going to have the slightly more negative charge. The one that's farther away from fluorine is going to have the slightly positive charge. So I can look at a molecule itself. In the water molecule, I can say, oh, the whole molecule is polar because one side is negative and one side is positive. If I look at this carbon dioxide molecule, I can't take this positive with one line out away from the negative. Because I can't, the bonds are polar, but the molecule's nonpolar. Does that make sense? So I can't, with one line, cut that positive away from that negative. Because I can't do that, the negatives on each side, I can't get a positive or negative side to that molecule. Okay? If I look at this one, the hydrogens and the carbon make up the positive side of this molecule, so I can actually cut this molecule and I have a positive and negative side. So this molecule is polar. But this molecule where the chlorines are surrounding the positive, I can't cut that carbon away with one line. Does that make sense? So that's a nonpolar molecule. The bonds are polar, but the molecule is nonpolar. Okay? We all right? Do you have an aha moment? Okay. So if I can cut with one line and get that negative away from the positive side, so this whole side was positive, this whole side is negative. But this one I can't, here's my center, it's in the center. If I could do a circle, but I can't do a circle, I've got to be able to cut it. And that circle's in the center and the negative's on the outside, so I can't say the center's positive, the outside's negative, that's not going to help me with a polar. A polar means I have a positive and negative like a magnet, side to side. Okay? All right, so polarity. If we go into FET, we can actually play with the polarity of the molecule. This is a really awesome thing. If we have time, I'm going to come back and do it. If you have time, go to it. All you have to do is FET, molecular polarity, in a search engine, and it comes up, and you can actually play with it, and it shows real molecules, 3 atom elements, and you can actually see the actual polarity of the molecule moving. If we have time, we'll come back and do that. I'm going to go forward to make sure that we get through everything that we need to. So, type of bond is determined by electronegativity. Let's see if we can figure out what type of bond this is going to be. So, lithium right here, 0.98, and fluorine on this chart is 3.98. So if I subtract those two, I get 3.00. What would that tell me on the electronegativity difference? Is that ionic, polar covalent, nonpolar covalent? Ionic. So we should be able to say, oh, that's ionic, easy. Okay? I want you to do the other 3. All you have to do is subtract the 2 numbers and then figure out where it goes. You okay? Yeah. Okay. Copper's right here, oxygen's here, nitrogen's here, oxygen's next door, hydrogen's here, and fluorine's right here. Okay, what do we get for them?
So, is the second one polar?
It is polar. This one's polar covalent. What about no? Nonpolar covalent. Okay, what about the last one? Ionic. Okay. And it's not going to write down there in my corner. There we go. All right, so fairly easy. If you're given a chart, you can really quickly just subtract them, and then you are going to need to know these divisions, though. Okay? All right, so it's not really, there's not really a, this one is actually 0.5 in your book. There's not really say, here is this and here is this. It's sort of an increasing character kind of thing. So the increasing character of it being ionic or increasing character of it being more sharing. There's not just a point where say, oh, these guys share for all the time. Does that make sense? It's a continual band kind of thing. All right, so classification of molecule of polar and nonpolar. The polarity of the individual bonds, I was talking about that as we were looking at the molecules. If the two elements are different in a bond, there is a polarity. If they're the same, then it's a nonpolar bond. If the molecule itself has a positive side and a negative side, then you've got a polar molecule. If it doesn't, if there's no way I can cut it with one line to cancel those, get those dipoles on one side or the other, then I don't have a polar molecule. And you need to be able to look at that and see that. Okay? So you need to make sure you're looking at the shape of the molecule, because the shape of the molecule will allow me to cut those lines or not. Like water was bent so I could cut the oxygen away, but ozone, or SO2, is a little bit bent so I can cut that. I was trying to think of another one. BeCl2 I can't cut. Okay? All right, so let's see what we can do with this. We just talked about water, and because water can be cut, I can get a negative side and a positive side. Boron trifluoride. Well, let's do, I think it starts at the top. Hydrogen chloride, polar or nonpolar? I was a little nice and I put the dipole moments on there for you. It is polar. Okay, what about ammonia, which is NH3? That one's also polar. Okay, what about, and you got to be careful with that one because as you draw it, this is what it's going to look like when you draw it. And if you don't know that nitrogen actually gets sucked out because of those unshared pair of electrons, you'd think you can't cut nitrogen away. So you got to know the shape in your head. Okay, what about boron trichloride? Or boron trifluoride, sorry. Polar or nonpolar as a molecule? Good, it's all in one plane so I can't cut it. What about carbon tetrachloride? I hear polar. Is it polar or nonpolar? It's nonpolar. I can't cut that carbon away. What about carbon monochloride tetra? I can't remember the name of this one. Anyway, what about this next one? That one is actually polar because I can cut that chlorine away from the rest of it. That's positive. Okay, because carbon hydrogens will be taking the positive where chlorine will be the negative. Yes? Because I can only use one line. I could cut one chlorine off, but there's still 3 chlorines down here. So that wouldn't work. Okay, all right, going forward. Focus on health and medicine. So you need to know a little bit about how we've got these polar and nonpolar molecules that we're using in our bodies and around us. So first one is hydrogen peroxide. Hydrogen peroxide actually looks like this. So it's a little bit different than water, how it's shaped. Okay. If you look at a molecule that's built of it, that's what it looks like. And this is what? Polar and nonpolar as a molecule. You got to be careful because this is actually polar. Can you see that? You can't see it here on the first drawing, can you? But on the second drawing, can I cut the hydrogens away from the oxygens? Yeah. So you got to sort of think in your head, how is this going together? Okay? And that's a little bit harder. Okay, acetaminophen. You need to be able to look at something like this and say, okay, wait a minute. Where are my negatives? Where are my slightly negative parts of this? Well, my slightly negative parts are right here, right, and right here, and right here. Those are my slightly negative parts. Is there a way I can cut those away from the rest of the molecule so that I have a polar molecule? Or is it too mixed in and won't be? This one is a nonpolar because it's got all the negatives around the outside, so it's going to be a nonpolar. Okay, ethanol is another one. Ethanol looks like that on paper. Okay, when we draw it, we put the Lewis dots in there. We go, okay, but when we make it, this is what it looks like. Well, guess what? Here is my negative, and it can be cut away from the rest of the molecule. So I am going to have a slight polar molecule there. acetaldehyde is what, after you drink alcohol, that's what's produced in your body. That's what give people hangovers. And so ethanol is drinking alcohol. Acetaldehyde is what your body makes with ethanol, which is causes the hangovers and stuff. This looks like this. This one is actually a very polar molecule because the hydrogen is gone. And it actually is extremely polar and can cause a lot of problems. You drink ethanol, it oxidizes, becomes acetaldehyde. It attacks the liver and attacks the brain and causes cancer. So that's one of the side effects. Okay, so going forward, here's a B6 vitamin. She will be using these big molecules, and you need to be able to say, okay, what part of that molecule would be negative? Look at things that are close to fluorine. Oxygen's always close to fluorine. Nitrogen's always close to fluorine. So those are ones I narrow in on and say, okay, right here would be a negative. Right here would be a negative. Right here would be a negative. Here would be a negative. Here would be a negative, and here would be a negative. Well, if I look at the overall molecule, this little section over here, this top half, seems to be a little bit negative. So it'll have a slightly polar. The reason I say slightly is because this nitrogen's here too. That nitrogen has an unshared pair of electrons and it can be a little bit polar. But with all that oxygen on that top part, that part of the molecule is going to be more negative. Okay? All right, so then we get down to study for the test. While I'm not here next time, you need to make sure you make it through all the homeworks. You need to make sure that you do all of the Learn Smarts. And you need to make sure that you do the pre-lab. The pre-lab is in this right here. So I won't be here at all on Friday. So you have the whole period to work on that. Okay? Yes? So Learn Smarts are due the day of the test, or actually the 11:49:59, the day before the test. Test is Monday the 12th. So so you guys meet our Friday, so we have Tuesdays the lab, and then we have Thursdays the follow-up or review, and then Monday will be the test. So it's a real short unit, but it's not that hard. Okay? Please make sure you make it through your Learn Smart. So you have 5 minutes right now. I would get Learn Smart started. You should be able to get through Learn Smart and be done. I'm not going to do the DSD Canvas Nearpod because we didn't have enough time to work, but I am going to be doing it in the future. Okay? So open up your computers, get it started, get going on it. Do not waste this time. And I probably will not put up your guys'